good. Thanks so much for being here this morning. My name is Julie Demuth, and I'm a researcher at the National Center for Atmospheric Research, which is one of the sponsors for this Understanding Risk event. And I'm absolutely thrilled to have everybody here this morning and to have a panel of amazing speakers who I'm going to introduce in just a second. But first of all, I just wanted to set the stage a little bit for this session that we've put together this morning, which I've titled, and we joked about this last night, a 50% chance of an effective forecast. Last night when we were kicking off this Understanding Risk session, we decided to do these Ignite talks, which Simone said is part of the UR, I guess more generally the UR tradition. So I gave an Ignite talk on this stuff last night, and I'm going to repurpose some of those slides here this morning, even though I know some of you were there last night, but not everybody was. And I really just wanted to set the stage for why we're talking about the things that we're going to talk about here this morning. Because over the next couple of days, I mean, there are a lot of really interesting understanding risk sessions that are going on. And when you think about risk, it encompasses a lot of different ideas, one of which is risk communication. But what is risk communication? When you think about this phrase, what are some of the ideas that come to mind? It encompasses a lot of different things. And when you think about it, it's actually kind of fun to go around and do this. Start paying attention to all the little risk messages that you get in any given day. Some of them are kind of silly, and these are actually real. Do not hold the wrong end of the chainsaw. So clearly somewhere along the lines, somebody decided that it was necessary to provide this kind of information to people. Or I'm sure you could look at the cups that we all have from the coffee break, and it will warn you that the coffee that you're about to drink is actually hot. But other risk communication messages are much more important. Whether it's alerting us that we might be eating something that could cause an allergy, or to remind us to not text and drive, or any other host of risk communication messages that we receive. Well, what about weather forecasts? We might not necessarily think about these as forms of risk communication, but really they are. They're a way that we are made aware of something that might be hazardous or that can cause harm to us in any given moment. There are a lot of different types of weather risk communication, and even though a forecast like today, I mean, it's gorgeous and beautiful here in Boulder, that might not necessarily be communicating a risk. There are a lot of really high impact weather events. I'm sure everybody here in the room is really well aware of Hurricane Patricia that just formed on Tuesday as a tropical depression, and then 24 hours later was still just a tropical storm, and then 24 hours after that was a Cat 5 hurricane with winds up to about 200 miles per hour, and made landfall along the western coast of Mexico last night. So these are messages from the National Hurricane Center talking about how potentially catastrophic this hurricane was, warning about this extremely dangerous major hurricane, life-threatening flash floods, mudslides, et cetera, et cetera. Closer to home, earlier this week we actually had some snow in the high country, which is actually really exciting. The high country is beautiful right now when you look and see it. But this was also posing a risk to people who were driving, I guess this was on Wednesday, people who were up going into the high country on I-70, and a lot of different crashes, and they had to close I-70 eastbound for some period of time. Now another hazardous weather event that really requires risk communication that we're all too familiar with here in Colorado is flash flooding. And this is going to be the hazard that we're really going to focus on more in this session here today. And flash floods, they're actually, I pulled this because they had all sorts of flash flooding in Texas, and actually I think it's going on even still this weekend, partially enhanced by some of the remnants of Patricia, I think, as the weekend goes on. Flash flooding is a particularly difficult hazard to try to communicate information about because oftentimes it's very spatially localized. Or it's a rapid onset event where when you get enough precipitation that overwhelms the basin, then that's when everything, all hell breaks loose, and you have to figure out how to communicate that kind of information at that very spatially and temporally localized scales. And then in terms of what those societal impacts look like, how do you convey that information to people? And we have a panel of people here who are experts in this, which I'm really excited that they're here to be able to talk about the research and the operational components of trying to understand and communicate this kind of information to people. And because even though we're getting a lot better at being able to capture the observations that we need to understand these types of events and to be able to put a lot of different risk communication information out there to people, it's still a huge challenge for those reasons that I mentioned. And so, just to kind of circle this back around, weather forecasts are an important form of risk communication because they're a way that we make people aware of these hazards and help them start thinking about how to prepare for and respond to them. And this kind of information is useful to a whole different heterogeneous group of people, whether it's us here in the room, our emergency managers, rescue personnel, even broadcast meteorologists. But as we think about how to improve those weather forecasts, how to improve that risk communication, we have to sometimes, and oftentimes, step back and think about what goes into that information. What is the state of the science? What do we know? What do we not know? What are our capabilities and what are our limitations? And have a candid conversation around that topic. And that requires really digging into the atmospheric science research and understanding the operational environment of the practitioner environment, where somebody like Daniel Will, who works for the National Weather Service, has an important role. So we're going to have a conversation here over the next hour and a half about how well do we observe the atmosphere? How well do we observe the rainfall? How well do we observe pressure and temperature and winds? How well do we understand the processes that lead to flash flooding? And then how does all of that affect how well we can predict it? And so I am absolutely thrilled this morning to have this amazing panel of people. I'm going to rave about them for just a second. Because these are researchers who are very much at the cutting edge. They're leaders in their field. They're young, wonderful people who I think are amazing scientists, but they're also really passionate people who love what they do and I think are excellent communicators. And I'm hoping that we can have an awesome, really informal conversation among all of us here as we kind of tackle this really important and exciting is probably not the right word. Maybe it's exciting from one perspective, but this important component and this important problem. And so the way we're going to run the session is we're going to have some remarks by everybody, and probably about 10 or 15 minutes, and then I think we'll just break into a very hopefully thoughtful and energetic discussion. We're going to start with Dr. Russ Schumacher, who is an assistant professor up at Colorado State, and there Russ leads this precipitation systems research group. He has, gosh, I don't know, how many students do you have, Russ? Six students now, and he has graduated several with masters and PhDs. Russ really is like I said, he's a leader in trying to understand what are the ingredients that lead to heavy rainfall events. What are those processes, and how well does that help us understand these events and help us be able to better predict them? Dr. Kelly Mahoney is a research scientist. She's got a very long set of affiliations. She's with the NOAA Earth Systems Research Lab, but also with CU with their CERES group, the Cooperative Institute for Research in Environmental Sciences. And Kelly's also a leader in trying to understand these precipitation systems, but then also situate our knowledge both in terms of the historical climate and thinking about it in the context of climate change, but also trying to understand what is the capacity for how much precipitation might we possibly get in any given point or any given area. I don't know if I'm characterizing that well, Kelly. But in addition to thinking about understanding the precipitation systems, Kelly also does a lot of work in understanding what happens when that rain hits the ground. When it interfaces with the land surface, and so she's working with a lot of people and doing a lot of research on kind of an integrated hydrologic modeling framework. And then finally, we have Daniel Neatfeld, who is the Science and Operations Officer at the National Weather Service in Omaha. And Daniel is kind of, as I said last night, he's the boots on the ground guy. He's the guy who understands all the meteorology and who's benefiting from the advances in the science from people like Russ and Kelly. But he's the guy who's sitting there at the end of the day, whether it's at 3 o'clock in the morning or 3 o'clock in the afternoon, getting all of these observations and trying to assess whether there's really a flash flood risk, and then how to get that information out to people. Daniel also just spent 4 months with the National Weather Services. It's the Weather Prediction Center, so it's one of the national centers, much like the National Hurricane Center, that works on providing forecasts of high-impact precipitation at a national level for the forecast offices. So Daniel's really involved in trying to connect the research into that operational environment. So like I said, I'm just over the moon to have these people here today to be able to kick us off and talk about these types of topics. So with that, Russ, I will let you come up.
All right, well, thanks Julie, thanks everybody for being here, for the opportunity to talk about some of what we do. And so I'm going to start off here and I'm hoping this works out, working great. I'm just going to show you this movie to begin with. This is sort of a zoomed out perspective over Colorado and surrounding states of all the National Weather Service radars over about a 5-day period in September of 2013, which folks here in Boulder probably remember quite well. But I think looking at it in this perspective sort of frames a little bit of what we're going to talk about here. So it's just started over there. So here we're on the 11th of September and now going into the 12th here, and that there's some very heavy rain in Boulder here, and it sort of continues through that period. But this, kind of looking at it from this perspective, you get a lot of sense for all the different kind of scales of motion that are going on in the atmosphere. From sort of this big picture swirl over, sort of centered over Utah, that you can pick up that things are kind of spinning around generally, but then much smaller scale stuff that with storms that are forming and moving around in different directions and so on and so forth. And so, when we're thinking about trying to, say, understand the magnitude of the rain that fell during this week, which was historic for this area, and also kind of thinking about how you would forecast that, we have to keep in mind kind of the different scales that we're looking at here. So kind of starting about now is when the heavy rain near Boulder really gets going, and sort of the heaviest period there. But sort of when you look at it in this perspective, that heavy rain near Boulder was actually kind of a really small, in the context of this map, it's a pretty small blip on that map. But that's what we care about. And if we're going to worry about a historic flood, then that's the sort of situation that we need to be able to give some sense of the details of, and maybe not just a sort of general perspective, but really get into the details that I think then Kelly and Daniel will focus on here going forward. So I'm going to, so kind of talking about precipitation too, it's a slightly older quote from 10 years ago, but it's still true, and I'll show sort of but that also that we've improved on this too. So when we think about, quantitative precipitation forecasting is sort of a jargon term, but it's essentially, saying that it's going to rain, 2.1 inches at Boulder, tomorrow or something like that. And it turns out that this is really hard, and I'll try to explain sort of why that's the case a little bit, but also that we've made a lot of improvements in this, and that there are sort of between improvements in observations and understanding and models and that sort of thing, that we're at least moving in the right direction on this, but that it remains that this is probably one of the hardest things to forecast is rainfall, and especially rainfall in the warm season. Okay, so I'm going to show one equation. If you've spent a while since you've had math, this hopefully will be very simple, because it's actually a very simple equation, but it helps us understand kind of what goes on in to get extreme precipitation or that eventually might lead to flash flooding. So the P on the left-hand side of the equation is the precipitation, how much is in your rain gauge in your backyard or whatever. And so it's just a function of, kind of to break it down at its simplest level, it's a function of how hard it rains. So that's the R. Here it's R bar, so it's like the average over some period of time, multiplied by how long it rains, right? So this is pretty simple. That kind of the simple way to put it is the most rain in your gauge is going to happen when it rains hard and it rains for a long time. Right, and so we sort of saw this in the 2013 case, and I'll show some other ones here in a little bit, that there were periods where it rained very hard, but also it rained for a whole week. And so the D part of that equation was really a big factor there in that case. But if you're looking at different weather situations, sometimes it will rain 4 or 5 inches in an hour. And so it doesn't really matter how long it rains. If it rains that much in a short period of time, then you have a lot of rain. Or it can be like the 2013 case where it was more modest rain rates, but it just didn't quit for a long time. So some of what we do in our group to look at these kinds of issues is say, look at those radar loops at the beginning, and you can kind of make some conclusions about this. And these are sort of situations that really make it possible to get both R and D to be big in that equation. So the laser works too. So for example, just think of this as sort of a cartoon picture of a radar image, and everything here so this is the heavy rain here, and everything in this picture is moving from left to right. And so if you live somewhere along here, every time one of these little red blobs passes over, it's going to rain hard, and they're going to keep passing over, and so the duration is going to be long. And so, I mean, there's lots of different ways you can kind of put the weather together to have this situation happen. But sort of to break it down to these sorts of situations, it gives you a sense for the, some of the things that we look at. Okay, so I'm gonna move sort of from that and to more of the forecasting or prediction side. And this is there's a lot going on in this graph that I think is really interesting. And I like to show this like in my classes and stuff too, but it tells us a lot sort of about the state of forecasting heavy rainfall. Or this is sort of maybe not super heavy rainfall. This is, it's heavy but not that much. So it's an inch of rain in a day. So that's a considerable amount, but not like necessarily a flash flood sort of situation. And so these are from forecasts made by numerical models in the green and the blue bars, and then by human forecasters in the red at the Weather Prediction Center where Daniel was recently. So this is on the axis here goes back to 1993 through last year. The y-axis here is something called a threat score that the details aren't that important at this point, but a perfect score is 1. So the higher the score, the better, essentially. So there's a bunch of things to look at here. Maybe the first thing, pointing out that the perfect score is 1. You can see that the score is nowhere near 1, in general. So we don't predict rainfall perfectly. You all know that already, right? There's been days where the forecast was for rain and it didn't rain, or vice versa, or if you thought it was going to be a little bit of rain and it was a lot, or something like that. So anything like that will make the score not 1. So that's sort of the first thing to look at. But probably, sort of then from there, you can see that the sort of general trend is for this to go up with time. So that's really good, right? That means that the forecasts have been getting better. Forecasts today are a lot better than they were in 1993, for example, or even, 10 years ago. So that's a good sign. And another thing that you see in here is that sort of all 3 sets of bars are getting better over time. So that's encouraging. But you may also notice that the sort of distance, of the higher that the red bars are here above the green and the blue has also sort of stayed pretty constant with time. And so what this is telling us is that the numerical models that we use to forecast the weather, that's in the green and the blue, have gotten better, but that the human forecasters have continued to add value above that. So the human forecasters sort of continue to be better than the models, through time. So sort of it's telling us that people still put this picture together. Obviously, a big input to the human forecast is those model forecasts, but the humans can sort of still add value to what the computers tell us. And there's a lot of reasons why that's the case. Anyway, we could talk about that for a whole hour or something too, but primarily the things in kind of these heavier rainfall situations where sort of humans can put this whole picture together in a sort of a more complete way sometimes than the computers can. Okay, so we'll kind of keep that in mind there. And then I'm going to show just a couple examples of forecasts and sort of think about what they're telling us and how to improve. So this is a forecast that was issued on Monday morning, September 9th in 2013. It's a map of precipitation that would fall over the next week in Colorado and surrounding states. And you can see there's a big bullseye over Boulder and Larimer counties. And remember that the heavy rain sort of started on like the night of the 11th, really kind of in earnest, and then for the next several days after that. So this was sort of 2 days before the rain started and for the few days after that. So from one perspective, you can look at this and say this is really an outstanding forecast, and it is sort of by the standards of weather prediction. This is an outstanding forecast. It highlighted several days in advance that there was going to be really, 4 inches in a week is a pretty big event around here, especially in September. And the location is sort of spot on. But those of you that were here know that a whole lot more than 4 inches of rain fell during that period too. And so, so this is, it depends on your perspective, sort of how good of a forecast you consider this to be. But sort of from the standards of what, kind of our field, this is doing pretty well, but clearly it's also not perfect in a lot of ways. I'm going to skip over that one for now. So I'll just show you kind of a couple other examples, and I think Kelly and Daniel will probably get into these concepts a little bit more too, that we can do forecasts, and so Julie's title of the session sort of gets at this, right, of percentages and that sort of thing. So the traditional way that we've made weather forecasts, for precipitation, say, well, there's two different ways. One is, there's a 30% chance of rain or 50% chance or whatever, and so we call that probabilistic, right? It's based on probabilities. Or you can forecast sort of a specific outcome, which we refer to as deterministic. It's like you're putting one number on it, sort of thing. And so this is from the, and so that the map I showed here is a deterministic forecast also. And so this is from the South Carolina case a few weeks ago. This was a deterministic forecast. This is the units here in millimeters now, so but you remember that 25 millimeters is an inch, so 385 is like 15 inches or something like that. So anyway, this was a forecast that was made by the Weather Prediction Center for 15 plus inches of rain, which is like going out on a limb and saying there's going to be 15 inches of rain over the next few days is a pretty bold statement, right? And so, and as we'll see, this turned out to be, there was at least that much and quite a bit more, it turned out. But you could also, so as we've talked about, the score on that graph is never 1, right? So to sort of say there's going to be 385 millimeters there and not 387 or 375 or whatever is sort of ridiculous, right? Like we know we can't make that, we can't be that precise, it's not possible. So in some ways we're being kind of misleading by putting out a forecast like this, but people also want a number and they don't want to look at 20 different maps or whatever. And so what we're trying to do, I think, a lot in our field is recognizing that we can't this is sort of unrealistic in a way. You want to put it in terms of some other framework, like probability. So this is from an ensemble of forecasts that NCAR runs. It's probably like the state-of-the-art, like about the most advanced system there is right now. I mean, it's still kind of experimental and they're working on it, but it's a pretty great system. And so, you can make a map like this that is the probability of 10 inches of rain in 2 days, over this region. And this all comes from a bunch of computer models. But anyway, so this is basically showing like 100% of those computer models are putting 10 inches of rain over South Carolina there. So it tells you sort of the same story, but maybe in a slightly different way. And then if we look at what actually happened, this is on the same color scale as this one. I mean, again, that's a pretty outstanding forecast of saying there's going to be 10 or 15 inches of rain there, and that's what happened. And the location is slightly off there, but it's pretty outstanding again. Now, this is sort of a great example. There are others that are not so great, and that's what we're looking at in research. So I'll just kind of wrap up with one other example here. So I've showed you that we've improved forecasts for all sorts of reasons a lot over the last 15, 20, 50 years. But we agonize over the times when we get the forecast wrong, and that motivates a lot of our research. And so this is just another example from that same ensemble. This is from back in May. This is that NCAR, state-of-the-art system. And so this is probability of 3 inches of rain here. So it's really focusing in. So you can see 100% of those models are putting 3 inches of rain here, kind of in the Oklahoma, Arkansas, Texas border region. And you'll note that none of them are putting much rain down here in the Houston area, or there's maybe one that has that much there. And it turned out that this was a huge flash flood in the Houston area on this day. And actually they got nowhere near 3 inches of rain up here. And so these kinds of issues still happen. And this is the challenge that people like Daniel deal with all the time, is that some of the time the models nail it and it's outstanding. And then other times it leads you to, I mean, this is still probably a useful bit of information here. The models are putting out lots of rain somewhere, and that's sort of what we saw in the Colorado 2013 case. The models were putting lots of rain somewhere. It just wasn't clear whether it was going to be Boulder or, you know, out by DIA or whatever. And then if you're trying to know what the flooding is going to be like, then that's a huge difference, right? If the rain falls in Jamestown, it gives you a very different result than if it falls on downtown Denver or in DIA. So these are the kinds of cases that we're still trying to do better with and improve as we go forward. So I'll stop there. I don't know if we want to do any questions now.
Clarification questions or burning question for Russ, we can ask it now. Otherwise, we can move on to Kelly. So anything for Russ? Otherwise, we'll have a great discussion. Okay, yeah, go ahead.
Oh, yeah.
I got one. And I am by no means anywhere near like a meteorologist, but like just maybe just real quickly or broadly, what are like the most value added components that your guys' research looks on improving right now?
Yeah, that's a really good question, and it's sort of, I mean, the easy answer is maybe a kind of cop-out answer, but it's also true, is that it's sort of, we need all of it. So there's things that we still don't observe very well in the atmosphere, especially conditions above the, so we have lots of observations at the surface, right? Weather stations at airports and in your backyard or the top of your school and that sort of thing. And then satellites are looking down, giving lots of information too, but sort of the moisture profile, like how much moisture there is in the atmosphere above the ground, but in the lowest, couple thousand feet or something like that is hugely important for how much rain falls, but we don't measure it very well. You have, a weather balloon twice a day in Denver around here, and that's pretty much what we have, but it's, Denver at 6 a.m. can be very different than Boulder at 3 p.m. sort of thing, and it may not be. So, and then that's all the stuff that goes into the models, and then stuff like, in a model, the smaller the scale that it is, like the smaller the process you're looking at, the harder it is to deal with. So like our models are not very good at saying, you essentially have to predict like which, more or less which droplets in the cloud are going to form raindrops that are then going to come to the ground. And we don't have, models don't we can't run them at that fine level of detail. And so you have to sort of make some educated assumptions based on past cases and that sort of thing to get at those. And so that's a big problem too. So it's sort of the whole gamut from observations to models. And then how do we make sense of this stuff and interpret it kind of from just from like a forecasting side, but then also like if you're trying to tell an emergency manager or whatever a situation, then that's an issue too. So I think sort of an all of the above kind of thing.
Real quick on what would be the optimal remote sensing technology, either improving existing technologies or a new sensor that could really help you guys right now with your research? Yeah,
I guess I would say things like measurements of moisture above the surface and the structure of it. So we actually do one remote sensing measurement of moisture that is really valuable is you can use the GPS satellites essentially and the sort of the way the radiation goes between them to calculate the moisture in the full depth of the atmosphere. And so that's a hugely important measurement, but it doesn't necessarily tell you that it's sort of all concentrated near the ground or lots of it's at mid-levels, and that kind of stuff is important too. So I think, like here in Boulder, Radiometrics does microwave radiometers, so you can get a better picture of that. There's a lot of these kinds of remote sensing technologies that are pointed in that direction. But then we need to figure out how to get that information into a model too, and that's tough.
Yeah. Are you guys looking at or connected to any of the folks that are starting to look at cell phone towers and attenuation of signals as potentially useful?
Yeah, not really myself, but I think it's a very cool idea. And also cell phones have barometers in them now, and pressure is a good measurement. And so people are kind of starting to try and take advantage of these, see if we can get much out of these kind of crowdsourced weather observations, so to speak.
Okay, I think we'll move on to Kelly, but Russ, I think you did a fabulous job sort of laying the foundation, and you started to really raise some issues of challenges of being precision versus accuracy versus confidence, and I think that's kind of an area where we can have some really good discussion as we go on, so.
No, Russ, that was perfect because Russ and I have pretty similar research, I think, backgrounds and interests. So I'm going to attempt to highlight a couple of maybe slight differences in what I do and then turn it over to Daniel, because I know, at least I personally am really interested to have the discussion and learn from everyone here as well. So as Julie said, my name is Kelly Mahoney. I work just across the street in the NOAA, our Systems Research Lab, but all the words under my title really is because I'm a part of the cooperative institute between the University of Boulder, or University of Colorado Boulder, and NOAA. So the flavor of the work that I do, again, kind of topic-wise, is very similar to Russ, but is really sort of a go-between type of position between operational folks like Daniel and research interests at the university. So I just sort of listed a laundry list, essentially, of the kind of work that I do kind of as it pertains to the Front Range of Colorado flood risk. So I came out to Colorado about 5 years ago to take a postdoc studying Front Range flood risk, and spent the first couple of years looking at old historical events, and then 2013 happened, and so I've been really busy with great stuff ever since, for better or worse. So I look at sort of the climatology of heavy rainfall in Colorado and how that might change under changing climate scenarios. Kind of going back to that, what Julie actually just said about understanding the confidence that we have both in short-term weather forecasts and where that confidence comes from, where it is, where it isn't, how you communicate that, and also on the long term. So we look at climate change projections and how confident are we in those, and just how much of that confidence do you want to capture in long-term planning scenarios. Russ sort of started to get at this too, the way that the field of meteorology is moving is going into probabilistic frameworks. So you run a lot of models, and at what point are you running so many that they are no longer useful? Where do you kind of curve that? How far do you take that in different space and on different space and time scales? Against how stakeholders, from short-term weather forecasters to long-term water resources managers, dam safety. I work a lot with folks who do dam safety design and risk assessment for hydrologic hazards. So on very, very long time scales, how can stakeholders use what is really still cutting-edge research advances in a lot of ways to us, but there are and there should be more ways that we can sort of start to include some of that in decision-making processes. Some of the work I've done, again specific to Colorado, has looked at precipitation type, so whether or not precipitation falls as snow, hail, graupel, or rain affects the associated impacts and flood risk that you face from it. And then this topic that has been sort of new for me really in the last couple of years is, why, to say it very generally, why does sometimes, a little bit of rain will cause a high impact flash flood, and other times you get a lot of rain and it doesn't, and that kind of goes to just the first of two areas that I was going to talk about today, and that is coupling meteorology with hydrology to really better understand flash flood impacts. And so my background, I have no training whatsoever in hydrology, and never really intended to go into that field. But you can really only study flash floods for so long until you realize that the rain coming in is only half of the equation. And so the sort of slant my work has taken in the last couple of years is to work with hydrologists and folks that know how to do this very well and to model this very well, and start trying to bring precipitation and all of its uncertainties into a couple hydrologic framework. And I'm starting just to wrap my own head around all the uncertainties in the hydrologic part of our science, which there are lots there too. So this animation is just a a very simple example of computer weather model precipitation, so rainfall falling on the ground in the blue and green shading, and the bright red where there was a lot of flooding. This was a case that actually happened back east in North Carolina. And then the little branches on the ground are obviously creeks and river, watersheds. So this model is capable of taking rainfall from the atmosphere, dumping it on the ground, and distributing it not only into the streams themselves, but also, I think for people who are hydrologists, what makes this model a little bit different is that it also does things on very small grid scale. So it also can tell you things about surface inundation, certain things that are a little bit different than simply taking a bunch of water, dumping it into a stream and seeing where it goes. So this is sort of a new tool we built at NCAR, but it's also being wrapped into a lot of the National Weather Service and National Water Center goals in the next couple of years. We understand that we need to get into this framework to really get at flash flood impacts and again that on the ground risk assessment. So I think the other thing I wanted to say is, this sort of maps out a short-term weather event, and again, the National Weather Service really is moving in this direction. This also has a lot of impacts for, going back to what I was talking about before, sort of longer-term risk assessment. When you talk to people at the U.S. Bureau of Reclamation or the state and local agencies that do longer-term planning for hydrologic, hazard risk assessment, rainfall only gets them so far as well, and I learned that in the first couple of years. Working with these stakeholders, it was sort of like, oh, well, that's really great that you have this state-of-the-art meteorological tool, but what we really care about is the water at the dam, in the reservoir, what happens to get it there. And so tools like this are allowing us to more directly interface with those users. So the other part of this that I just wanted to point out is, again, going back to this idea that we need a lot of variations on a solution to be able to tell you just how confident you are in them. Some cases, like Russ was saying, are inherently very predictable. Other cases are much less so. And so not only from a research perspective, but also very much from an operational perspective, you want to know how confident you are, but you also want to know why you're confident in it, what part of the forecast is pretty confident, what parts aren't. And so this sort of coupled weather and hydrology framework, I think in the long term, we're again kind of starting this work, and this is a project that we're actually, Daniel and I and a number of people across the country are going to be working on. It's taking a lot of different rain forecasts, so a large ensemble of different short-term rain forecasts, putting them into this coupled meteorology, hydrology model, tweaking parts of the hydrology field so you can add different kinds of uncertainties. So Russ kind of talked about how you get, so those thumbnails up top, those little postage stamps are just different computer model forecasts of a given rain event. So you can change model physics, you can change the kind of observations that go into a model. You can get all these variations on a theme basically of the forecast, and it tells you how different all those end up looking like. It might tell you how confident you can be in your rain forecast. You can do something similar on the at the land surface interface. Like for instance in Colorado, a lot of times we get rain that falls on top of snow. We're notoriously bad at monitoring snow and having that information in our weather model. So maybe at the sort of land surface level, we say, this is what we think the snow looks like, but what if it was 10% higher or 10% lower, or it wasn't in this place, but it was in this place? So you can make those adjustments in the land surface interface and also run that kind of model in an ensemble framework. So all of a sudden, your spaghetti plume, so that little map there is just what stream flow could look like at a point. It's a very basic, forecast type or forecast display. You could start to get a lot of different estimates of stream flow. And this kind of goes back to how you use this and how you communicate the risk. How many noodles on your spaghetti pot do you really want? How many do users really want? It's going to start to make you feel really not confident after a while if you have like 200 and they're just all over the place. So the science going into this is trying to constrain that, making these perturbations to the atmosphere and the land surface interface in a smart way to get a value, to have value added in this uncertainty information. And then, how do you communicate that? How do you display it? That's going to be a major push behind this project that, again, we're working with Daniel and others in the National Weather Service on, is you know, gosh, these models can do all this and we can spit out all of these possible scenarios, but how do you use it? And how do you use it when your decision-making timescale is very short? So that's one, you know, thing that I've been doing. Oh, and this other map, so I'll just flip back and forth. This is ideally, you know, something where trying to get at impacts. It's very simplistic. It's sort of a GIS map of inundation, and so you would also want to take maybe a probabilistic view of, you know, the probability of surface inundation in very localized areas exceeding, say, 1 inch, 5 inches, whatever. This is very hard to get at. This is sort of like where we hope to be a number of years out. But again, where the field is moving, and I'm glad that it is, because many recent events have shown that's where the impacts end up lying. So this is the only other slide I was going to show, and again, just trying to have an opportunity to talk about sort of the longer term work that I do, but again, all very still based on flash floods. So this is
There used to be a little island right there.
This is basically how different dams in our region responded to the 2013 floods. I borrowed this from the Colorado chief dam safety engineer. He put this together and shared exactly where all of these are, but they're all fairly close to the front range. So I think after the 2013 floods, well, as they were happening, there was different, you know, kind of on social media or on Twitter, there were messages going out saying dams were breaking, and I think people thought it might have been very dire. And then luckily, it really wasn't. You know, no high risk major infrastructure ended up breaking, but there were a number of very small dam failures. So I just wanted to show that video because I had it available, and a lot of the work and some new work that we're doing over at NOAA going forward is working with the state of Colorado to improve their long-term risk management and the way that they, I guess, impose restrictions on dam owners to have them up to certain safety codes. They're going to be revamping that in the next 2 years, and so we're trying to add some sort of better science, updated data to the way that they do that. The nature of this kind of work, again, it really goes from short time scales to very, very long time scales. So people who build water infrastructure need to look at risk assessment very holistically, actually. So they, I sit in meetings sometimes where people talk about concrete for hours, and like the porosity of concrete. And so lots of things go into risk assessment for dam safety. And it's fascinating that weather actually is very only, in some situations seems like a small part of it, but weather is what will make a dam fail. And most dam failures are due to water overtopping, so weather forecasts, and people obviously, especially going forward, especially in Colorado, need to also say and show in a documented way that they took climate change into account when they do their longer term planning. So we're trying to bring all of these tools that I've talked about, these advances in short-term weather forecast models, on the ability to run known flash flood events in high resolution and understand where our certainties and uncertainties are, again, in the atmosphere and at the land surface interface, into a longer-term plan decision-making framework. And you know, the way that these dams were designed when most of them were built decades ago, unfortunately, not to necessarily worry anyone, but those methods haven't been updated since then, and that is much more due to, I'd say, policy and institutional memory infrastructure than it is to the state of the science. So we're trying very hard to bring some of these scientific advances in, but a lot of the stumbling blocks are very much, I think, what we're here to talk about today, is that it's easy for people in these institutions to say, well, look how uncertain you are. You ran all these models and these things were all over the place, and I can't possibly plan for this huge envelope of uncertainty, that would be very expensive. And so trying to have this back and forth ongoing discussion that, yes, it's back and forth, but hopefully you're moving forward together. Constructive dialogue where you say, yeah, maybe you don't get it right the first time, or maybe you don't plan for, I call it the maximum precipitation that could ever happen. There's a concept called probable maximum precipitation, and that's something that's very contentious in the water infrastructure framework. But so maybe you want to do a probabilistic framework, and I think we haven't talked about this yet, but we probably will at some point today. Imagine the 1 in 100 year flood, 1 in 1,000 year flood, 1 in 10,000 year flood. Useful concepts, not always easy to implement and practice, and can be misleading, especially on weather, when it comes to weather events and people's own memories and how that affects their decision making. So I could go on about this forever. I find it fascinating, obviously, that I won't go there because I think Daniel has a lot to tell us about how these decisions actually get made, and some interesting stories to share with you. So I'll wrap it up there.
Thanks, Kelly. Questions for Kelly as we transition to Daniel? She raised a lot of great issues. I have questions I keep writing down. So why don't we actually then transition to Daniel really quickly, and then that way we can segue to our group discussion afterwards.
All right, thanks. Yeah, it's great to be here. I live in Omaha, but I love to come to Boulder for a lot of different reasons. So really happy to be here. Julie mentioned that I'm the boots on the ground guy, so I'll get a little bit of a taste of that. And this talk's going to be a little bit different than what we saw before. I'm going to try to take you inside the National Weather Service and into an office, a forecast office, where we actually do the forecasting. So I don't work at I don't work at the forecast office here in Boulder, but I work at the one in Omaha. And it's great because Russ and Kelly did a great job of justifying my bad rainfall forecast. It's really hard. Trying to forecast rainfall, as you'll see, is pretty tricky, and it's something that we're asked to do a lot. It's the main thing that people often want to know about. And so, again, I'll just try to take you through a little bit of the process of what we go through. Again, I don't know if everybody knows that the National Weather Service is certainly part of the federal government, and this is our mission. So we come to work every day, and this is what we're asked to do, to provide weather, water, and climate data, forecasts, and warnings for the protection of life and property is the main thing here. So that's what we're tasked to do. Your tax money goes to help us to do that. So I'm going to take you back to September 9th, 2014. This is an event that I personally worked. I was in the office this day. This is the official forecast for Omaha that came out. And it says here, Omaha, 3:41 a.m. So this was the forecast that was issued early that morning. And I asked you, how well do you make decisions at 3:41 a.m.? And it speaks a little bit to one of the challenges that we have as human forecasters, is that obviously the weather's always ongoing, so we have to work shifts 24/7. And there's a lot of interesting things about 3:41 a.m. It's just a difficult time to be awake and to be making decisions, and this might be your 7th shift in a row that you had to work overnight. But nonetheless, that is part of what we have to do. And we'll talk about some issues about flash floods that occur in the middle of the night, which is often when they do. The one that I'm going to talk about, fortunately, did not. But there's issues with that, with the fact that they occur in the middle of the night, a little bit more vulnerability, people are asleep, and so forth. But in any event, this was our forecast for that day. And we basically had cloudy with showers and thunderstorms in the afternoon. The chance of rain was 90%, which is pretty high, right? And we didn't explicitly say this in this forecast, but in another one we did say 0.61 inches of rain was what we had in the forecast. So that's a fair amount of rain. You know, it's not super heavy rain, but it's not bad, right? It's not light rain by any means. This is another type of a forecast that we issue. You know, this one back here is all text and it's not very fancy. This one is what's on our web. It's called our weather story. So it's kind of a quick at-a-glance forecast. And we've got a few different images up here. This one's just showing a little bit about the weather pattern, where the fronts are, and so forth. Down here, we do mention, it's kind of hard to read that, but it says heavy rain through 7 p.m. So kind of a big area of rainfall that we're expecting. And in this case, they've got over 2 inches of rain. This is actually for a longer period of time. But in any event, showing that we could have some heavy rain there. But then on the right side, we've got some severe thunderstorm forecasts. And this is basically saying that in this area we could have some severe thunderstorms. And then in particular, we have a tornado risk map down here. Chances are a little bit low, 10%, which isn't really high, but it actually is pretty high for getting a tornado. So this is fairly significant. And again, I want to point to the title here, Severe Storms Possible. When you talk to a lot of students that go into weather, a lot of them say, I want to forecast tornadoes because they're cool. I want to study tornadoes, they're really neat. You don't get a lot of them that say, I want to forecast rain. Wes gets a few. We talked about how heavy rain is, it's kind of neat, right? But it's not like really cool. It's not really sexy, we say. So sometimes, and even meteorologists get kind of hung up on that. It's like we're really expecting thunderstorms and hail and high winds, especially the cool tornadoes. And we know that thunderstorms produce rain, but sometimes they take a little. The heavy rain takes a little bit of a backseat to the severe weather. We see this all the time, actually. It's kind of a problem. So it's something that we're working on a little bit. But again, that's kind of what we're expecting. So I'm going to take you inside the office, like I mentioned, and this is a snapshot of our weather office here. It's got quite a bit going on. You can see fairly busy. There's about 10 people in the office that day. This is about 3 p.m. on September 9th. So again, we're expecting thunderstorms, and when we are, we usually bring a few more people in and keep a few people over and so forth. So 3 p.m., you can see a lot going on, as I mentioned. These are all the forecasters. They're looking at things, looking at the atmosphere, looking at radar, looking at satellites, and so on and so forth. But you can also see we've got some things going up on the wall. This is just a big picture of our radar loop. We'll look at that in a minute. And then we've also got news channels that are on these what we call situation awareness displays. We're trying to see what everybody else is talking about. We're trying to see why. So that's a little bit of what's going on there at 3 p.m. And you can see, in particular over here, that we do have storms that are coming in. We'll take a closer look at that. So at 3 p.m., forecast is pretty much on track. I say, here's what we know at 3 p.m. We knew that we had a line of storms coming through. That's right there. Again, I'll take a closer look at that. And then we've just got a lot of other things that we're looking at that indicate, sure enough, storms are firing up and they're moving through. We've got a lot of moisture. This is just one of many images we look at, essentially just saying that we've got a lot of moisture in place. So, Russ kind of talked about some of those ingredients. And we did indeed have ingredients for thunderstorms and in some cases heavy rain. So again, things are sort of on track. We know that the city of Omaha is going to get some storms. Nothing in this area right now looks especially strong, so it doesn't look like huge hail or tornadoes or anything like that. But we also know that as thunderstorms move through, we're going to get some rain. All right, kind of zooming in on that radar image that I showed, this circle is basically the downtown part of Omaha. It extends a little bit further west, but that's what that is. And that's a pretty good looking line of storms, fairly strong. This is just our radar reflectivity and indicates where we have heavy rain occurring. But as you'll see in a radar loop in a minute, this is moving through. And again, for Omaha, this is, I wouldn't call it garden variety thunderstorms, but it's nothing really outstanding, but nonetheless, it does show that we've got a pretty good storm moving through. Here's the loop. Hopefully I can make this work. And again, it's nothing too exciting, but it does show that this line of storms developed and is moving east through the city. A little bit of a radar outage there. There's a little gap there. I'll look at it one more time. Just to kind of show you that the storms are moving through. So when Russ talked about training thunderstorms, where they sit over the same area, this was not really doing that, right? It's moving along about 35 miles an hour or so. So again, we expect a burst of heavy rain, but nothing that would really be too much of a problem. So I show this picture again. Again, here's our little news stations. We're also monitoring social media. And this is what comes in. On the news, these are two images that we saw from local TV stations. And you can see a lot of cars that are underwater. This is actually a rescue squad that did a little bit of rescue from a couple cars in that area. And this is a tweet. Saddle Creek Road's now Class 2 rapid, going under Dodge. Pretty sure those cars are stuck. But this kind of gives you an idea that we don't really know what's going on out there at 3 o'clock or 4 o'clock until we start getting some of these reports. So it shows you that this is a pretty important way of finding out what is going on. This is from the Omaha World Herald. This is the next day. Just to kind of give a quick description of what we had. High water, late Tuesday afternoon, trapped vehicles, so on and so forth. Firefighters helped the mother and 3 children from their blue Toyota Sienna. I'm not sure the significance of that. But blue. We don't know the color of the truck here. That's helped too. But in any event, we're going from fairly normal looking line of thunderstorms moving through Omaha to this. So it was somewhat surprising and could be a little bit of a problem. Why did that occur? Well, we had 1.43 inches of rain in a 20-minute period, and that was measured by a rain gauge. And in a lot of cases, these rain gauges underestimate that heavy of rain. So anyway, 1.43 inches in 20 minutes is a lot of rain for that amount of time. And especially in an urban area, we can end up with those kinds of conditions. So not a tremendous amount, 1.43, but in 20 minutes it was a lot. This is just a quick glance at the overall rainfall map. But it does show you the variability. This was 3.43 inches. Again, this is a 24-hour period in Omaha. But we had 5.5 just north of Omaha and 1.39 on the southwest side of Omaha. So tremendous variability in rainfall amounts from those storms that moved through. Pretty tough to pin that down. So a couple concluding thoughts. It often is the rate. And Russ talked about P equals RD. Rate is really, really important. And I talked about this notion of can the basin drain the amount of water that just went into it. And it's really, really simple, but you just think about your bathtub as a basin, and you know that your bathtub has a certain amount of water that can drain out of it. And if you pour more water into that bathtub or basin than the drain can handle, then it's going to overwhelm the bathtub or the basin. That happens when we have flash flooding. It happens when we have city streets that can't drain that much water off. So that's basically what we're talking about. So high to moderate rates over several hours or days, like we had in Colorado in 2013, can really be, that's where we can get 12 inches of rain. That's the difference between the 2-inch rainfall forecast and the 12-inch rainfall forecast. And it's really, really difficult to differentiate between that. To forecast that high of a rate over that long of a period of time is very, very challenging. One last thing here is we generally don't predict those very well at all. Just a couple quick words about prediction in general. Forecasters and the science of forecasting, it's certainly doing well when it comes to forecasting atmospheric changes that are pretty gradual, things that are pretty natural. The sun comes up and the temperature warms up. Those things we do really pretty well at. When it comes to really sudden changes in the atmosphere, those are probably beyond the limitations of the science right now. We're getting better, but it's those sudden changes in the atmosphere. When you think about rainfall, start time, the end time, again, this is in your backyard, intensification changes. So that ultimate rate, the amount, those are all very, very difficult things to predict, as Russ and Philly alluded to. So because of work that they're doing and a lot of other researchers, we are certainly getting better. But we do have a long ways to go.
Great, I think you guys timed that really beautifully. It's just after noon, so we have about 25 minutes here to have a conversation. And like I said, I think that Russ and Kelly and Daniel painted a beautiful picture of what we know and what we don't know and what some of the challenges are. And I would love to open it up to questions. Anybody has them? Otherwise, I can jump into some. Yes, please.
In your modeling, can you accommodate some of these externalities? For example, Boulder, of course, had water, but it also had an incredible volume of soil in that water, not only due to slope, but due to fire damage to the upper hills. Do the models have a way of numerically accommodating what-if scenarios with those external impacts?
Currently, no. Not in a real-time nowcast forecast sense. Where some of those higher end cutting edge hydrologic models are going is to account for those processes. And I guess again, without formal training in hydrology, my perception from working with these groups in the last couple of years is that it's still at a very elementary level how that gets done, particularly when you have to combine the volume of water coming in from the atmosphere with how the soil gets brought up and dumped out. So in an ongoing situation sort of case, it takes the Daniels and the forecasters at the forecast office to mentally put that together to say, and they're very good at doing this, but it's really hard to say, we know that there were burn scars, up in North Boulder from last year. We know how much rain is coming in, or we think we know about how much rain is coming in. Qualitatively, we expect enhanced risk, but quantitatively, we're not there yet.
Okay. Could I throw in on that one a little bit as well? So you're probably aware of this, but the National Water Center, which is where our colleague who does the forecasting, it's like the mothership, if you like. They have a research and development interest in developing a better understanding of triggering thresholds for debris flows. And a lot of that was stimulated, as you know, by the Boulder event. But there's some prototyping going on out in California right now, and I'm assuming they've been able to get a lot of data in the last couple of weeks with some of the recent big debris flows they've had up in San Bernardino's. But there's a general interest in improving the utility of the National Weather Service forecast to be able to give folks at least some indication of when those thresholds might occur in response to the rainfall and runoff forecasts that are currently put out.
Yeah, they're definitely still in an R&D mode, right? I mean, the debris flow modules in that hydro model, it's going to take a little while to get there.
Very much R&D, but some of the disturbances that you guys are experiencing right now in the move to the water center, that might actually speed that up quite a bit.
Absolutely, yeah. So for people who are interested, there's the National Weather Service and the national group that runs models and things, and just within the last year, there's a new National Water Center that opened, and it's down in Tuscaloosa, Alabama. And I think even though they're just getting ramped up there on a national level, that has added a lot of motivation and just to really fast track a lot of this work. And so some of the things I was talking about, coupling the hydrologic model with the operational computer forecast models, that probably would have been on a much slower time scale had this new national center not come to pass. And so it's been successful so far, even in just pulling together hydrologists and meteorologists and asking these questions. And so the debris flow thing was being done in very small separate camps, I think, before, and now people are kind of pulling together and saying, this is a need, and it's a nearer term need than we thought. So I didn't mean to be overly pessimistic. I don't know how far off it is, but it's not there yet, but it is being developed for sure. So optimistically, stay tuned, I guess.
And one other thing that we didn't talk about today, kind of going back to your original question, there is this idea of flash flood guidance that the Weather Service, actually the River Forecast Center. So, Weather Service and NOAA, there are many different entities. We talked about the Weather Prediction Center, but there's also 13 river forecast centers, and then there's 122 local weather forecast offices, so it's sort of like this tiered system. But the RFC produced flash flood guidance, and it's a very, I don't know how high resolution that information is at, maybe like 2.5 kilometers maybe. But it's sort of a forecaster that they updated on a daily basis about how much rain you would need in a given area to cause flash flooding. And some of that, going back to your question, can incorporate burn scars as part of, for those areas you would have flash flooding that would occur with less precipitation. So I don't know if you guys want to add anything to that.
No, that pretty much nailed it.
Okay.
Yeah, it's really limited in terms of, it's critical that we understand what the ground can and the basins can, how much water they can handle, but again, the limitations of the science don't really allow us to understand that all that well. It's very much a guess and estimate of how much, say 3 inches of rain falls in a 3-hour period. Can the basin hold that? There's some estimates on that. It's pretty crude.
And those estimates will incorporate rainfall, previous rainfall, so it will incorporate soil moisture to some extent too as well, right? Another area where we don't have really good observations. Yeah, exactly. That kind of goes, I think, one of the questions that was asked of Russ, what kind of observations are needed? Soil moisture is one of those that we just don't have really good observations of. So, good proxies are there.
It seems even if the estimates are pretty crude, if we get a better estimate of what the triggering thresholds are, so that you can at least put out a warning. And then the other part of this is better understanding how that plays out as a physical process. In other words, we've got nice coverage of 100-year floodplain maps for the whole country, which gives people a lot of information for mitigation and emergency response. But what we saw in the Front Range was a very different process play out. So better modeling of what the actual implications of the debris flow, changing the channel and actually changing that flood boundary is, to me, it seems to be the second key part that could be really, really helpful for communities.
Yeah, it was on the other end of the spectrum, sort of, I know that this is all very short-term focused, but is there any practical interface between what you guys do and, say, the seasonal projections around ENSO and around El Nino for this region, and the knowledge that we're, if you look at the papers, likely to get a much wetter year potentially? Yeah, that's,
I mean, in a basic sense, yeah, like that, those things are things that we can look at and all, and certainly that it changes. I mean, what it does is it may change sort of the odds that in a given winter or whatever, or winter period summer, that you might be more or less likely to get a big event. But it's sort of that the influence of say, and so I mean, you know, on precip really anywhere, and especially around here, it's pretty. It's not a huge shift in the odds one way or the other, and so and even in places where it is a bigger change to that, doesn't mean that a big event can't happen, you know, in the flip side phase or whatever.
but would you see that feeding into, say, the difference between the forecaster projections and the higher skill level that's shown there versus the lower projections? Kind of gut sense of what's going on regionally? Or is that more of it just a familiarity with local weather patterns and burden stars?
Probably like on a weather flash flood time scale, it's event for event, and obviously if you had a really wet season because of ENSO impacts, then that will go back, you know, feedback in everything we just talked about. We know the soil is wet and so on. I mean, there are other things that I think the weather community, the weather and climate community are asked to weigh in on, like especially in California and out west, it's called like a forecast-informed reservoir operations or forecast-informed planning procedures. And so there are people who, again, going back to the dam example, will choose to operate their dams differently if they anticipate a big El Nino year. But from a short-term impacts perspective, I think it's mostly event for each event kind of independently.
But would it be better to actually jump to ensemble forecasting? Basically, you have the tools, you have the models, you have the data. So suddenly you can actually run ensemble forecasting and basically start changing parameters after parameter and see what's coming out. So it will actually potentially answer those questions. And also, second little bit on that is you using kind of one type of modeling if you go to the distributed type of models, which basically now the computer processing is there. So if you do the distributed type model and you start dealing with sideways and uncertainty zone, maybe there is not needs too much to observe of the soil moisture and all of those. And you can actually bring that in, and those tools actually exist. They don't develop; they actually are on the market. So you could actually improve your systems much, you know, by basically marching much more faster forward and start dealing with the data which we actually don't know what's coming because we don't have that many sensors, we don't have that many observation data. You know, I know a couple of states are going to the Mesomed, you know, Oklahoma, New York State, and so on. So you can actually start building those processes, and you don't have to, let's say, spend too much research on the modeling tools per se. I don't know.
I mean, part of it too, you guys obviously jump in here. I think one of my knee-jerk reactions is that, well, first of all, why don't you just run an ensemble? Sure, I think we'd all love to run a huge high-resolution ensemble out to months and see what comes out, but A, it costs a lot of money, and B, it might not be that well informed, especially if you don't have great observations to constrain it at the relevant time scale. So I don't know, you asked a lot of really tough questions wrapped together there.
And I think sort of in a general sense, you're right, is that the limitation at this point is not sort of as much the model infrastructure. I mean, there's lots of improvements that can be made there, but it's the it's the sort of limitations of observing the inputs to those models that is the bigger limitation, which I think is kind of what you're trying to get at, and that's where partly it's a problem because like we just have insufficient observations and data, but it's also chaos, right? We can get that better and better and better, and you can't sort of get around the fact that the atmosphere is chaotic and that there's large differences that result from small differences, sort of thing.
You're chasing basically a really small scale.
Yeah.
Because you're doing flash ones, but you don't have sensors in that scale, so you have obvious disconnect.
Yep.
And isn't it better basically start investing there in those observations, because you can have super duper models, like garbage in, garbage out. So maybe that instrumentation is probably our problem right now than anything else.
It's a huge problem.
And as far as I know, because I know some gauges are now, USGS gauges are offline and so on, and it's facing whole nation. And those are the most important data in this case.
Yeah.
And we're just shooting ourselves in the foot.
There's not very many gauges that tell us how much rainfall in a 15-minute period. A lot of them, a lot of the precipitation reports that we get across the country are once a day at 7 a.m. So it doesn't really help you when you're trying to forecast the flash flood that's occurring now.
Oh, yeah, I'm just saying scale and the resolution is not there. So you're kind of chasing something which probably it's going to be hard.
Yeah.
No,
I mean, I
it's
think,
absolutely
yeah,
right.
I think meteorology or atmospheric science is still data assimilation, so assimilating the different kinds of observations in the atmosphere. That's still a really pressing problem for atmospheric scientists. We've been doing it a long time relative to the state-of-the-art, the current state-of-the-art hydrology models. Hydrologic data assimilation is now, I think, really ramping up as a critical thing, but it's starting a little bit behind where maybe the atmospheric people are in terms of, okay, the data's out there, but how do you get it in? What about catchment sizes? And there's just a lot more questions there. So I don't know, totally agree, but but my sense is that it's an even tougher problem at that on when it comes to putting those observations into the short-term hydrology forecasts.
I mean, and you can think of sort of from like a practical perspective, bureaucratic perspective or whatever too. It's not easy, but it's easier for one government agency to buy a huge computer to run forecasts than it is to have, Colorado go and put rain gauges, and you have to talk to the person that owns that property. Can we put a gauge, and it's a big like sort of, effort, and maybe people in Colorado are more okay with it than people in some other state or whatever, and so I think that's part of the reason why we don't just have gauges everywhere too, is that it's like a lot more sort of effort and money and all. Maybe it's not more money, but it's more sort of logistically challenging to do that.
One quick comment about modeling too. I mean, there's a lot of excitement, and the science of modeling efforts has really exploded. It's great, but they still generally stink. They're not great, and they're good for certain things. But for your backyard, that stream that runs through your backyard, tomorrow, how much rain is going to fall? It's not good. So we have a long ways to go. We can talk about, we should model this, we should model that, but we need a lot better models if we want to really crack some of these hard problems.
And I think, we talked about this before, it is so place specific. Russ and Kelly and others talked a lot about the South Carolina event. And that was an event that I spent some time with the WPC forecasters, like Russ said, all the models were saying at least 10 inches of rain, because we really understood sort of the regime that this kind of flooding was going to happen under. But you contrast that with the Utah flood event that happened, in September, where it was 1.5 inches of rainfall in 30 minutes in a specific slot canyon that then caused 20 deaths, I think. So the kind of processes, the kind of systems, or the sort of the structure of those types of events, and particularly where they fall, makes such a huge difference. And we're not even tackling the questions of communication. So even if you look at that picture that Daniel showed, even if you started to know that you were getting rain rates in some of those areas, how much lead time do you have? And then think about the whole communication network. How do you get that information out to people? Daniel didn't even bring up the fact that there was a school bus sitting there. That flooding was happening at 3 o'clock in the afternoon on a weekday. How do you get that information out to people then, that you might have flash flooding in this area, and what can they do about it?
So how do you communicate? So we understand, many of us understand that there's just, some things just aren't knowable. Or, and so how do you communicate, we might say probability, but how do you communicate that kind of knowability to the public? And then this I only have a partially formed idea, and I'll just see if I can go at it. But then how do we do that? And what is our obligation, or what do you feel your obligation is to getting that right to connect, whether to risk communication around general trends in climate? Like, how do we manage the negotiation between the precision around weather now, and I'm not a system, I'm a computer scientist, so I'm not using all the words that you would use, but you kind of get what I mean. And then how do you then communicate, what risks do we take, or do you take as communicators, in getting the weather accurate prediction as accurately as you can, communicating knowability, and not putting at risk some other bigger knowability or communication around climate and climate change? Because that's all taken as assumptions in what you know and do. But we have this other conversation we have to have with the public too. So I don't know.
Yeah. I'll say something about the first thing that you asked, because that's something I think a lot about, because that's sort of like some of the research that I do is like figuring out why certain situations are more predictable than others, or why like forecasts are really good in this case and not this other one. But sort of that, that is a pretty, kind of thinking like you can say that, you can say, well, sometimes we know really confidently that this is going to happen, and sometimes we have no idea. But like that's not a very satisfying. It's like satisfying at a very basic level, but not like on any given day. Like if you had a tornado hit your house or flood in your town, like that's not a very satisfying answer. That wasn't predicted well. It's not very satisfying to say, well, this one was a hard one, so we missed it. But these other times were better. So I think that I don't know. I have no answer to the question of how we do it, but I think it's a really sort of challenging problem.
So how do you communicate precision of science and not have people not lose faith in the abilities of science?
Yeah, I know in other like talks I've seen you give, you've talked a lot about like the relationships you sort of foster with the people you work with, and I know you've done some of that too. And so that at least has to be, I think that has to be some of it, is if you can sit down and have a conversation about it.
Right. Ideally, if you could have somewhat of a relationship with the person you're talking to, or the community you're talking to, there's a little bit of trust there. Words like confidence, we're really confident that this may occur, or some of those phrases can help a little bit with that.
And then I don't know if you want to talk about the sort of climate context more, but that's a hard one too, I think.
Especially when you're talking about, we're all talking about flash floods here on very short space and time scales, and all of the problems we're just predicting them tomorrow, much less, within the envelope of climate change uncertainty. So, the way, sort of the approach that I've taken with others in the last few years is to take known events, so events that impacted a community very strongly, like the 2013 front range floods, and you kind of push on that from a number of different atmospheric perspectives and say, if the climate were to change in this way, how much stronger could that event could have been? And but that doesn't really get to like really the short-term predictability of it. So that's kind of it's treating each of them in isolation. To do it all at once is really tough. And yeah, you do have to appeal, I think, very much to the communication aspects, to the human psychology of the situation. I think a lot of work has been done very, very specifically on hurricane forecasts, and Julie showed some forecast discussions using the text to point out this is confidence is growing in a certain situation, but the hurricane forecast framework has really been scrutinized in the last several years over do you draw a track with a line, like a forecast track? Do you provide a cone? People say they want the cone, but if it's too wide, they don't like it anymore. They still pay attention to the line. So like people want uncertainty, confidence, but they also want precision. And that's the really tough part that Julie, is particularly an expert in understanding what people say they, like there's, that is definitely the really hard part. So you can,
Is there such thing as post-risk communication?
By that, do you mean, a lot of people talk about using these as windows of opportunity. I don't know if that's what you're talking about.
I don't know. After it was done and you didn't know and you kind of half knew, and so then whatever happened, happened. So, is there something conceptualized in the community around that idea of, well, after the fact, this is what we knew, this is what we kind of know could happen again, and we have no scenarios? I don't know.
That's a great question. So I don't know how much like the Weather Service gets an opportunity to do this, but we had interviewed some of the media people here in Denver about flash flood risk communication, and they talked a bit about how they don't do a very good job of closing the loop, and they're trying to do better at that. So if they issued a flash flood warning, if somebody doesn't experience that flash flood, but other people did, they're trying to go back on air and say, okay, I know that you guys didn't see a flash flood, but it did happen over here. Or if it didn't happen, here's why it didn't happen. So there's a little bit of that going on, but this is also where the Weather Service in particular, they don't have a direct line. Well, they have a direct line. They put a lot of information out. They don't really get much feedback from their users, other than maybe traditional partners like emergency managers and media. But members of the public, they don't get a chance to really communicate with them directly, at least not at a very broad scale. And that's one of the disconnects that we have with putting a lot of this information out and not really being able to evaluate what people are thinking about it. So that's where
I don't think there's sort of like a systematic, like there are times when this happens really well, but there's not sort of like a systematic, like this always happens. So a colleague that all of us have worked with, and I'll admire Bill Hook, has often talked about the idea of having, so, I think in weather we do this still a lot better than a lot of other like communities that do predictions and that sort of thing, but still there's room for improvement. So he always uses the example of the National Transportation Safety Board, that if there's an aircraft accident, there's a systematic like thing that always happens, that the investigators will go out and do this and talk to these people and sort of figure out exactly what happened and what went wrong, and then that it has a mechanism to go right into like changing that in the future. And we don't really, we do that sort of on an ad hoc, like this, there was this big flood in Boulder, so there's tons of researchers here, and so it sort of happens like by proximity or whatever, but like if the same thing happens in, a small community in southern Utah, that just may not happen because there's not like a framework to do that. And obviously to do that all the time would be much more costly and everything else, but
yeah, so there's just, I think, a lot that like Russ is talking about. We spend a lot of time talking about observations of the atmosphere. So this is another type of observation, right? We need to be able to go in and find out what did the forecasters know, what information were they looking at, what information did they put out, what did the members of the public, and what kind of information did they have, what did they receive, what did they think about, how did this fit into their risk perception and their decision-making processes. So, for the most part, we really focused here on the meteorology, but how that links, how that produces risk communication, and then what people do with that information is something I think that we're really lacking observations on as well. I wanted to
jump in this one because it's something which kind of frustrates me extremely, because coming from Europe, if I walk around the river, which I was born next to it, you have old mills, 300 years old, and there's marks of the flood, 20, 40 of them. And, as a young kid, you understand, okay, some water was someday here. And 10 years ago, Noah actually was trying to walk into coastal communities in Connecticut. And basically, they were putting high water marks, which is basically saying, potential storm surge during the, hurricane category 2 or 3 or whatever, and so on. Within 2 hours, they were escorted out of the community by sheriff and mayor. They don't want to know people about the risk. They don't want to decrease the value of the property, and they are not welcome anymore to any discussion. And working with FEMA on many places was always the same. How we can decrease the risk on the map. We know there is a risk, but how we can decrease on the map so we don't have to pay flood insurance. So it was about the money, about development, about cost. It was never about the risk associated with it and basically working with the communities. If something like this happens, are you ready? And basically those communities are less and less ready, and they're building floodplain more and more. So we're increasing this.
Yeah, well, now you're hitting on all those other variables that make this much more difficult, right? And that happened around here after Lake Thompson. There were certain areas where they were restricted from building on, and then after some years, enough time goes by, people forget. There's sort of what we call an apathy of vigilance. So you stop worrying about that kind of stuff, or you want to make money off of that land. And so at the end of the day, it's not always just about the forecast, like Kelly was talking about. Sometimes there's all these other variables that affect what information we're willing to put out there, and whether or not we're willing to put people at risk. And there's a lot of other researchers who work in the vulnerability and kind of hazards literature or hazards fields that focus a lot on those types of questions. So
Paraphrase around that, water's bipolar market, flows uphill towards money when there's too little of it, and downhill away from money when it's too much.
on that positive note.